Okay, good morning everyone. My name is Vladimir Gurevich. I am the technical lead of customer engineering here at Barefoot. And before, as Chang mentioned, I was working at one of the biggest companies which designs the Ethernet switches, and I was also doing customer engineering, and I was responsible for architecting the APIs there. And as the most nice part of my job was actually teaching the courses to our customers, discussing how the chips work and how to program them and so on. So now we are kind of trying to establish something very similar here, first about P4 and later about some of our devices. So it's kind of might be a little bit difficult for me to talk after Chang because he told you so much. And all the concepts are there, but what we'll try to do is to kind of go a little bit more systematically, just to make sure that you get more confidence in the language. And I will also try to point out some of the things that you might want to think about in the course of your research. So the first thing we will go through real quickly, again, P4 concepts, just in a slightly different manner. So I'm not going to go through the same animations that Chang showed you, but it's important to understand that what P4 really does, it programs the pipelines. Devices can consist of various number of pipelines, and that device architecture can differ. But in general, the pipeline consists of these four very important components. So these components, by the way, can be optional. Depending on how the device is constructed, they might or might not be present. But P4 has certain different sections in the language which allow us to describe those pieces. So first, where we start, the pipeline is the parser. And so the job of the parser is to take the serialized data from the packet, because the packet is just a series of bytes, and can basically separate individual fields so that the program can find them regardless of at which offset those fields are. If, for example, you are trying to implement some P4 code to run, say, inside Linux kernel, where the packet might already be parsed and represented in the structure with individual fields inside there, then you might not even need the parser. Then, of course, we have a sequence of match action tables. That's probably you would think that almost every P4 program would have, but I've seen situations where people only use the parser section of the P4 program because what they really want to describe is programmable parser. So what is important is that all these match action tables, they operate on metadata. So the way all modern switches are constructed so far is that there is what we call a metadata bus, which goes from one end of the pipeline to another. And so that's what carries the data, and that's how those different stages of the pipeline can actually talk to each other. Think of this as registers in the CPU, right? So in all modern CPUs, the only way you can pass a result from one instruction to another is through a register, right? In the older days, memory was faster, so you could do it through the memory. But nowadays, only through the registers. So this is a very similar thing. And in fact, if you think about how in the real compiler we have, for example, allocate the fields inside that metadata, it is a very, very similar problem to how like say a C compiler allocates registers for the C program and the CPU, except that the problem size is much bigger. Okay, so this metadata bus carries both the headers of the packet in the parsed form, as well as all the intermediate results. It carries it through the pipeline, and so those match action tables operate on the metadata bus. And then there is a component that people don't talk much about. It's called Parser, and that is the component that takes the headers from the metadata bus and serializes them on the wire. So even though the current specification of the language doesn't talk much about this component, what we see is that this component is actually not as simple, and it requires certain programming if you want to really build a universal device. So right now, the Parser program is not written separately before, and it's kind of auto-generated from the Parser specification. And what it means is that, for example, if a packet comes in and it contains, say, TLVs, the order in which they will be output is not clear. So that's one of the areas where we're going to improve the language and provide certain mechanisms so that you can either algorithmically specify how the packet needs to be reassembled, or in, say, DMV2 right now, there is a simple fragment which just tells you the approximate order of the fields, and so on. Again, in some cases, there might be no Parser here, and I'll show you when those things happen. Okay? So as I said, all these are optional, and metadata bus, effectively, without it, probably nothing happens. So that's, I wouldn't say, is optional. Yes?
So just a clarification question. When you say bus, is that something we usually refer to in the architecture sense? You have a master, a slave, and then someone takes ownership of the art? Or is it just like a pipeline agency?
I think logically you should think of it as a set of wires, but if you look at how this is implemented in the actual devices, it's very, very complicated. So for starters, the current CPUs that we all use, right? It's 32-bit, 64-bit CPUs, right? I haven't seen 128-bit CPU yet. So these buses, they are usually measured in kilobits. Okay, so and that is why the switches are kind of so fast, because they operate on a much wider bus, even though the actual frequency is just comparable to regular CPU. In real devices, those could be registers, because you need to buffer. This data goes through a very long pipe. But in terms of, like, if you think about the buses, like the original PCI bus, where there was a master and slave and the arbitration and so on, it doesn't really exist in this world. Yes?
If the order that the TLB fields that are output are in an unknown order, then how does the next switch know where they are?
Well, the question is, what will the next switch do if the TLV order gets changed? Well, the beauty of the TLV is that usually you should be able to parse them regardless of the order, right? That's why they have type length value. You just see that's type number 5. Okay, it doesn't matter where it is in the sequence. So that's the beauty of the TLV, but that's also sometimes presents a difficulty. Depends on how smart the switch on the other side is. It's fully standards compliant. In some cases, when we talk about IP options, there is a special option which indicates that that's the end of all the options. So it should be the very end. So there are certain restrictions. Yes?
So in this process, packet comes into the buffer, and the first, say, n bits of the packet are going to get converted into metadata. The rest of the packet, the payload portion, that's going to get stored in some cell a pointer is going to be kept to it in the metadata, and when the deparser deparses the metadata, will it get reattached, or is there some other way it works?
Well, so from the P4 language standpoint, the header is whatever you manage to parse.
Mm-hmm.
Because if you didn't parse past a certain number of bytes, that's not available to you. At least the language does not provide that mechanism. You cannot say like packet byte number 58 or whatever. So technically, if we talk about how things are done on the real chips, normally yes. Normally they have cell organization, and typically whatever is not really required for processing is being sent away directly to the buffering mechanism while this portion is being processed. And that's really important, right? Because, you know, here we're talking about, you know, maybe 100, 200 bytes. The packet can be very long, and the Mac is just, you know, this processing starts, whereas the Mac is still, you know, busy trying to get this data. Some stuff, it kind of shows, if you look at the, by the way, how many of you had time to read the P4 spec? Just, okay. I can see that. So, like, if you, and that's okay, because otherwise I wouldn't be here. If you look at the P4 spec, there is a field in the standard metadata called packet length. And it specifically says if the device is in the so-called cut-through mode, then this field is not available. And the reason is that the cut-through mode in many devices, what it means is the device starts switching and processing packets without actually getting the whole packet in first. And so what might happen is the packet starts going, we do all this processing and this and that, and then suddenly the last 4 bytes come in. And what do the last 4 bytes of the Ethernet packet contain? The CRC. Right, it's not quite a checksum, right? Because we use the polynomial. And if that CRC is wrong, that's it. We just have to drop the packet where we were. Usually that means that some of the counters might be a little bit off, but that's the price people pay to have very low latency. Okay, so yeah, cell processing is, that's how typical things are done. Okay, so this is kind of the basic pipeline that P4 will program. And as I said, you know, different switches are constructed differently. So sometimes, so one thing is, for any Ethernet switch, you typically will need another component, which is sometimes called MMU, sometimes called traffic manager. It is basically the component which has certain responsibilities. One is queuing, the other one is replication, and third one is scheduling. So the reason is because typical switches have multiple ports, and so what that means is that there could be 2 ports or 3 ports or 100 ports trying to send the traffic into one port, because those 100 ports are clients and the 101st port is a server. And so if they send traffic relatively fast, we have to queue it. So that's kind of end-to-one relationships. And these devices, these components are very complex. Besides the fact that they have to queue, there's also various mechanisms for congestion control, for head-of-line blocking prevention, and so on. And by the way, there could be interesting stuff done in P4 if you think about that, right? So for example, what is congestion control? That means that if you have a method to obtain the queue lengths, right, you can generate the packet which says, hey, please stop sending me traffic, right? Or the other way around, if you receive a packet which says, please stop, you can extract, for example, the queue number and go and send a signal to that queue. Normally those things are done on hardware because we need, again, this to be very low latency, but it is possible to construct certain congestion control mechanisms using P4. The other thing is majority of the switches, they also support multicast, and broadcast is obviously just a variant of multicast, right? So we need it if we send a packet with a known MAC address, for example, or if we send a packet with a broadcast MAC address. So in that case, what it means is that the packet is stored in the human mechanism, but then it has to sit there for a while because it should go to one port and the other port. And sometimes if we talk about, say, virtual LAN environment and, say, IP multicast, that it means that the same packet can go out of the same port multiple times with different encapsulations. Anyone is familiar how IP multicast works in there? It's a long discussion, but that is something that very, very typical, right? So for example, or think about that you have multiple tunnels, and these tunnels, they all connected to the same interface, right? Because you connect to various different networks. So if you multicast, and your multicast is supposed to go to network 1, 2, 3, you put 3 different headers on top of the packet and send it out of the same port, same thing. So that's this block. And as Nick said, right, there is no way to describe the functionality of this block in P4 so far. Now, in other switches, here I kind of put the full pipeline here in some switches, and actually that's more typical. There is no real deparser at the end here, and might be no parser at the end here. So the data might be passed through here in the same kind of metadata form, let's say. That people, that's a very typical design as well. So it depends how you want to do. You can imagine other devices that could be programmed using P4, like for example a smart NIC. In a smart NIC, right, there would be no traffic manager. There probably would be just, you know, one single pipeline going that direction and that direction, and you just program those. So your programs actually, even the core of your programs will be the same. The details, how you interface with the outside world, will be slightly different. You can also think about a software, say protocol plugin, that you might want to put inside a thing like OpenWSwitch or any other software switch component that maybe Linux kernel, maybe in the user space. In that case, you might not need a parser or deparser, as I said, because it is just a protocol plugin, so you already know what metadata you have. So, but P4 allows us to deal with those things, and so effectively it has 3 different sort of sections. There are different sections of the P4 program. So the first section is data declarations. And so this section is really responsible for explaining and declaring how we'll deal with the metadata, what will be on the metadata bus, in what form, and so on. Then we have the parser program, and so the parser program allows us to program the parser, and currently it allows us to program the parser as well, so very nice, saves you some coding, but you know, in simplified form. And the last thing is the control flow program that really tells us which tables we have and what are the relationships, what are the conditions, how the packet travels through the pipeline. Okay, so those 3 sections, and we'll now go and kind of look at the constructs and see what can we do there. So far so good? Okay. So in the description of the constants, I will unfortunately be in a little bit uncomfortable place because the P4 spec is evolving. So what I'll be presenting to you is mostly the version 1.02, but I will also mention the important changes which are coming in the 1.1. The reason is because the behavioral model and the compiler that we are going to use during the labs, that's where they are. There's like it's 1.02 plus or 1.1 minus, whatever you want to think. And so I just want to make sure that you're comfortable writing the code that actually will be there. Okay. So as I said, 3 sections. So declaring your data, or your metadata for that matter, right? The other section is really programming the parser, and so the parser is a state machine. So we'll see how those states can be programmed. And also there are some other things that the parser needs to do. We already mentioned, for example, sometimes there could be a CRC or a checksum, so we need to know how to deal with those. And the last is really describing the packet flow. So describing the headers and fields of the packet, Chang already has shown you. It's very, very easy. So here's we declare the Ethernet header. As you can see, we use the a statement called header type, and it's very similar to struct or type def in C language. We have this field section, and you'll see that there are some other sections that can be used. And so here we just declare the size of our fields in bits. So once you've declared a certain type, like Ethernet T, you can create an instance of that using the header statement. So Ethernet T is the type, and you can create multiple of those. So for example, you can say either Ethernet, outer Ethernet, if you do things like, say, VXLAN or VPLS or something like that, right? So you will need more than one header. So here's another one, VLAN tag. Everyone is familiar with that? Okay. Anyone knows what CFI stands for?
Actually, it's called DEI, drop eligibility.
So DEI is when you use the inner tag, then it's called DEI. But initially it was called CFI, it's called Canonical Format Indicator, but no one uses it for that. It's really a drop eligibility indicator called DEI. So, well, just kidding you. Sometimes it's fun because you guys are still in the universities, right? And so there are lots of kind of important fundamental things that you need to do, right? But there's also like industry realities. And so very often I would interview young people who come in, and just to find out that the industry realities are still, very, very far away. So, okay. So here we declare the VLAN tag, and what I'm doing here, actually I declare an array of those VLAN tags. And so before you are allowed to create a header stack, so-called, or an array of headers. And so VLAN tags are a good example. MPLS labels are the other good example. And the reason is they can be handled specially, and they support special operations like push and pop, so you can add and remove headers very easily because you're doing a switching, so you need to pop a label, for example, or you need to send the packet further down, you can push a label and so on. So same thing with VLAN tags. People usually, typically when your computer talks to your network, you don't use any VLAN tags, right? So the packet just Ethernet header and then IP. But in more kind of real life environment, there could be one VLAN tag, and then when the packet goes out through a network provider, they will put another VLAN tag and so on. Okay, so far so good, it's very easy. So one of the differences that is coming is we're going to have a slightly different syntax here. There will be a data types, and so the syntax will look like this. And I didn't put it on the slide. So it will say bit 48. So that's a bit string. Or there will be another type called int 48. And so the difference is that on bit strings you cannot do the math unless you convert them to integers. And on integers you can do the math. And it's a very important thing that is coming into the language little by little, because right now P4 is really not a very type-safe language. Okay, so the metadata is organized exactly the same way. If you look at any device that I have known, really there is no difference between, if you look at the metadata bus, you can't really say what came from the packet and what are the intermediate results. So we use the same construct called header type. And here we declare some metadata. So here you can see the standard metadata that is defined in the current P4 spec. So when the packet comes in, the standard metadata will already have the egress port and will contain the value, some number which identifies on which port the packet entered the device. There is also this field called packet length, how many bytes in the packet, and as I said, especially in the ingress pipeline, this value can be very unreliable. So, but in the egress, it usually is present. There is also another field called instance type. So one of you asked Cheng about the ability to send the packet back for the processing. So it is possible to do, and there are several operations that allow us to do this. And most of the modern devices also have a very high-speed timers, just the counters that allow us to timestamp packets, and that is needed. Have you ever heard about protocols like 1588, for example? So there are protocols which allow switches to synchronize time between them very easily, and so that is based on the measurement of the delay. So the moment the packet comes in, usually in the Mac, sometimes in the PHY, it's timestamped. And there are some outputs. So there's the egress spec and the QID. Those are very typical. So the one thing that we'll also talk about, and you probably heard there were some discussions yesterday during the workshop about the standard model, right? The standard architecture for P4. It's really critical because if you want to write a really portable program, you need to know, like, what is the format? What do you really, it's a number, but what do you put in this number? How you would encode a multicast group, for example, or how would you encode a VLAN or anything like that? How would you indicate that there should be a certain knockout of the ports? It's all done in the traffic manager. So these things need to be defined, and so right now it's a work in progress. Now, what you do to declare metadata, oops, so when you do metadata, you use the operator called metadata, not header, even though we used header type here. And so there are some important distinctions. Why? So what are the differences between headers and metadata? So one difference is that when we declare a header, like we did on the previous slide, okay? Like here. It defined two things. It defined the size of the fields and which fields we have, but it also defined the order. So destination address, 48 bits. Right after that, without any gaps, follows the source address and so on. And here, even though the fields are not byte aligned, again, it's a very, very specific order. When you declare metadata, the order is totally not defined. That's one thing. The other thing that is different is that headers might be present in the packet or might not be present in the packet. So when we parse the packet, we find out which headers this particular packet contains. And so each header that we declare, it has a special attribute which says whether this header is valid or not. It's very important. If you try to match on something that is not valid, the match will not happen. So metadata is always valid. Typically it's initialized as zeros, but there are also, in the language, you can initialize to some other value if you want to. It will be initialized obviously every time the packet comes in. It's initialized because we're just looking at the life of the packet. And there are a couple of other differences. So one is when you declare packet headers, they can contain variable length fields, and metadata cannot. And also when you declare headers, the size of the header must be byte aligned. So it should be a number of, consists of whole bytes. So if the header, if you declare, say, my header is 3 bits long, then the compiler is supposed to pad it to 8 bits. Okay? So, and those things are kind of, I guess, part is just the real life experience, how people typically, like all the network headers that we know of, they are byte aligned, right? So, yeah, that makes things much easier when we declare them. So, as I mentioned, there could be variable length fields, and so one of the typical examples are the IP options in the IP tag. So, here's the header type for a regular IPv4 packet. So all the standard fields, and here we have the last field, which says options, and it has the length of star. In the latest spec, you will see that there's a new type called var bit, and it specifies how the maximum size here. Right, so the maximum size of IP header could be 60 bytes, and the minimal is 20 bytes. So we're talking about 40 bytes. So 320 bits. That's how you'll declare in the version 1.1 once it's released. So when you deal with variable length headers, usually you should be able to figure out what's the actual length, so that you can effectively skip over that variable part and go to the next header correctly. So that's this attribute. So here it says that you basically have to take the field IHR, IP header length, shifted by 2 or multiplied by 4, the same thing, right? And it says what's the maximum length? 60 bytes, right? That's normal. Why 60? Because we have only 4 bits here, so the maximum value is 15, so by 4. Okay. So now we learned how to define headers, so we can create our parse tree. So for the parse tree, it is basically just a set of states, and the parser is supposed to transition between those states. So here's how we do that. So the first state is called star. And there are a couple of operations that you can use here. It's a very, very simple thing to write. So you can say extract, and what extract means is take as many bytes as are supposed to be in this header, like Ethernet, for example. It has a type Ethernet T, so that's 16 bytes probably, or 14, I would say, right? And so just extract those and put them on the metadata bus. That's what the extract operation does. And then there is a special statement called return, which is probably a little bit of a misnomer in terms of the naming, but think of it as next state. That's how I would call it, next state. So what should be the next state? Well, we'll look at the ether type in the latest header that we just extracted. So that's the Ethernet. Inside there is the ether type field. And so if that ether type is 8100 and 8100, we need to go and parse the VLAN tag. If that ether type is 800 hex, we have to parse an IPv4 because that's an indication that it's followed by the IPv4 header. If it's 86 dB, parse IPv6. Anyone knows any other ether types? ARP, 806, MPLS, 8847, and so on and so forth. Here's the more interesting state, parse VLAN tag. So what we'll do, we'll extract our VLAN tag, okay, and look at the ether type there. So it could be that it says go parse IPv4, IPv6, but it also can be followed by another ether, by another VLAN tag. And so this can go for some time. So here we say, again, if the ether type is 8100 or 9100, so if you think about what this construct does, it's a masked construct. It's exactly the same as this one, just written in a different form. Then we'll go to the same state, so it kind of creates a small loop. How long will the parser sit here? Well, we know that we have declared a step of no more than 2 elements. So if we have 3 VLAN tags or 5 VLAN tags, it's not going to matter. We'll just parse the first two, and then the packet will be declared to be just a regular L2 packet. So we won't be able to parse more than that. And that's an important thing, you know, when you design your P4 program, you have a freedom and you decide how many you want to process. So that's how you declare the parser. And of course we can continue, and those states will be very simple. So if you want to parse IPv4, you just extract IPv4 header, and then you go to the English processing, and same thing for IPv6. Yes?
Say you have the maximum of 3 runtime space that's
On a couple slides back, I wrote 3. Here I wrote 2.
okay,
So
sure.
yeah.
So this means that once you call the parse VLAN tag, say 2 times, what is the last VLAN tag also has the next user type as VLAN tag?
So then you will just think that this is a L2 packet, which happens to to start with, you know, some data, right? So you will not be able to see the insides. So in other words, if we draw this, right, what will happen? So you have a 6 bytes, it's destination MAC address, right? And 6 bytes this source address. And then you have ether type. And so this might be 8100, right? So then we have our VLAN tag, and then another ether type, and it happens to be 8100, right? And so then we have another one, right? So this is VLAN IP. And so if you have more, again you have the ether type and it was 8100, well, sorry, so that then you will think that the payload starts with 8100, right? Or sorry, it's a part of the VLAN tag. I should have put the properties properly. So this is our Ethernet. That's the VLAN tag 1. That's VLAN tag 2. So suppose there was another VLAN tag, because this one is 8100. But we cannot parse anymore, so we'll just say, well, this is our L2 payload. Maybe there was an IP header here, but we're not going to get it.
Okay, but then like who does, so suppose I just lost the VLAN ether type is 8100 as well. Right, what happens to the parser? Because the parser, if you're thinking about a
It will just go directly to ingress.
Okay.
It will not consider this.
Okay.
So just to follow up on that, will the parser mark this packet as valid?
Yes. It is just,
Even though it's not completely parsed.
yes, it is just that you interpret. I mean, think about that. So you can have a packet, right? And so maybe it was, I don't know, 800, and there was IP, or maybe it was IPv6, right? But from kind of, if you look at that, if you just start looking at the packet, there was still L2 packets, right? So you can still process L2 packet. It's not going to be mischaracterized, right? It just will be processed more generically than it could have. And so the parsing depth is actually a very important characteristic, because, you know, typically parsing takes some time because you need to do it sequentially. And so the longer your parsing program is, the either, you know, for certain devices they have, like, if you parse up to a certain number of bytes or a certain number of headers, you can process packets at the line rate, and then, you know, you start, you know, getting more congested. So it's an important characteristic of what you do with your parsers.
So I have some questions about some keywords.
Yes.
So the word lateness, does it say that whatever you just extracted is the one
Yes.
that's being processed. So how do I say, can I also refer to something that I have already extracted?
Yes, if you wanted to refer to something that you extract, you can say just Ethernet because it's already there, so it's available, right? Or you can say like IPv4.ttl or something like that. So you can refer to that. And also, there is another word called current. So if you want to, for example, make a decision without extracting, that's also possible. And so that's how TLVs are being processed. So in your VMs, there's a directory tutorials, and there's an example how to process TLVs. So there's a special word that allows you to take a look at the current data where the cursor is, sort of, right, without necessarily extracting, because you need to decide what you will extract.
Okay. And the next keyword, does that say that I would use the next available slot for that specific header?
Yes.
Is that?
Yes.
Okay.
So that's here.
Yes. Okay.
Mhm.
And what's ingress?
So ingress is actually, we'll see, it's not a keyword, it's just the name of the standard control program. So in the switch, we assume that there are two standard control programs, ingress and egress, right? And so what you do is, once you say you transition to ingress, that means that you're out of the parser section and you'll go to the control section of the program and you'll start going magic. Yes?
My understanding is on your return select statements, the parameters can either be metadata or obviously header fields.
Yes.
Would you ever envision that could be a register field? That would be a feature request out of that.
I would think that all this is really depends on the target architecture, right? So if the so syntactically, so right now it's the registers are a little in flux in the spec, but as long as you can refer to a register using like an expression, you can put them there, and your architecture supports it, you should be able to. But you should remember that one thing is because we're gonna, because the parser by definition is a stateful thingy, you can probably, right? It has a state. We're going from state to state. So lots of, lots of things that you can, you might. I'm not sure what exactly you want to register for. But you
share
can,
your use cases. Why?
but you can do it by just having two separate parsing state, which kind of do the same thing, but you transition to them depending on the condition, right?
Yeah.
What
I guess
does it allow?
Well, I would just like to use a register for, persistent storage that I can change the behavior of my switch, of how it
Parser?
parses. Yeah.
Okay.
Well, to change how it parses.
Right. So I might want to extract more or less data depending on what I'm trying to do.
Yeah. So.
So as a backup solution, you could use resubmit. So resubmit is precisely there so that you can trigger parsing any number of times. And then when you do resubmit, you can actually attach the metadata that you have extracted, and the metadata can be derived from the pipeline processing. So you could have introduced register to produce metadata and then resubmit.
Yeah. That's my current approach. So,
Okay.
so that works. All right. Good.
Yeah, it depends. Like for example, some of the metadata here is also available. Like for example, based on your ingress port, you can go and do totally different parsing. If, for example, one port is the front panel port and the other one is fabric port. So you can say predicate the parsing of fabric specific headers based on the port. So, but as I say, the main thing is here is not so much what you can express in the language, but what your specific architecture will allow you to do. Right? So normally, for example, registers are stored in memories which are not present at the stage where parsers are. So in software, it's all easy, we can do it out. But in real life, it's slightly different. Okay. So as I mentioned, besides just extracting the fields, from time to time we need to do some calculations, usually verifying or generating the checksums. So here's the most typical case is the IP header checksum. So what we do here is the statement that was on the previous slide is very simple, right? We just, extract IPv4 header, but when we do that, what we need to do, we need to calculate the checksum to make sure that the header is okay. And so that's how we expressed it before. So we specify the list of fields that are supposed to participate in the checksum calculation. And then we specify the calculation. So we say that this is the list of fields that need to be checksummed. That's the algorithm, and that's the output width. So the checksum is 16-bit wide. And then we say that in our header, the field IPv4 header checksum, it's not on the list, right? Because it's not part of it. It's a calculated field. So when we are in the parser, we're supposed to verify that the checksum is correct. And similarly, if we are in the deparser, so we're about to generate the packet, the device will know that it needs to update the IP header checksum using the same algorithm. So that's kind of where things start a little bit more complicated because it's a real world thing, right? So that needs to be done. Fortunately, we don't have to do it for Ethernet CRCs. So that the Mac will do it for us. Last thing is sometimes you need to use more than one field when you do the select. And so P4 allows you to do that. So here I kind of showed you a more real-life parser state. So how we actually extract IPv4. So besides extracting, we also have the ability to use the special action called set metadata. It's available only in the parser. And the reason is sometimes, depending on your particular P4 program, you might want to have the values of certain headers in the intermediate metadata fields. What is used for, say, if you have a P4 program which can deal with tunnels, when you do your, say, L3 or L2 lookup, you might want to do either to do this lookup either based on the inner headers or the outer headers, right? And so you don't know in the beginning whether you want to terminate the tunnel or not. So what we do is here when we parse IPv4, and that's the other header, we store those values in those other metadata fields like lookup IPv4 SA and so on. And then if we decide that we're going to terminate the tunnel, we'll take the values from the inner IPv4 header and copy them here. And the table that way stays the same. We'll only look at these metadata fields rather than directly to the header. But back to the return select statement. So when, for example, we want to do a layer 4 parsing, we need to make sure that we are dealing with a header with the very beginning of the IP packet, right? Because the L4 headers, they occur only in the beginning of IP packets. So if the packet was fragmented, then it doesn't make sense to look at the fragment to parse the layer 4 header. So that's what we do here. So we check that, first of all, the fragment offset is 0. So that means that we're in the beginning of the packet. And that the header is a standard header, so it's only 5 words long. If it has any options, usually it's not a good idea to try to parse layer 4. And then we look at the protocol. So not just the protocol field, but all 3 fields. And so what we do here, we just need to concatenate them. And in P4, you can put underscore in between the digits, and they don't matter. It just makes the numbers more readable when you put a constant, and that's what happens on the select statement. Any questions on the parsing?
What if you have a field that's not 8 bits? You cannot concatenate those packs numbers.
Well, you can always concatenate. Huh?
The
You might, they might not be nibble aligned if that's what you mean, yes? Then that is actually one of the kind of, that would be one of the constructs where a little syntactic sugar, as people who build compilers typically say, would be very convenient. I agree. So as I mentioned, there is a component which is also programmed by those statements. It's the deparser. So the fundamental assumption right now in P4 is that you should be able to parse whatever you generate. Okay, if you follow this assumption, that means that if you take your parsing program, it will describe your deparser. It's kind of the reverse statement, right? Now, but as a result, what happens is right now, if you really want to be able to generate some headers which you never intend to parse, you have to do some workarounds and put some fake states in your parser program and so on, which I really don't want to teach you. but if you have such a situation, I can show you how to do that. So, as I mentioned, it's one of the interesting areas in the development of the language that we need to be able to define the parser cleanly. Okay, so the next part of the language are actions. And so we have really two types of actions. One are called primitive actions, which are done in the hardware and just defined by this, the spec. And you can have composite actions, same way like we create C language functions out of the multiple statements. So here the typical, at least some of the actions that are available. So first, some very simple actions like no op and drop. Actually, no op is really simple action, right? It does nothing. But drop is a very interesting action because the current spec is a little bit vague about how exactly it's supposed to be implemented. So, for example, the question might be, if you drop a packet, will the subsequent tables that you still haven't gone through see that packet, or will they not? Right? So, this is another area where I think, you know, the language will require some refinement. There are the most used actions are modify field and kind of some of its variations. So modify field basically can take another field, and in version 1.1 and in the system that you'll be using for your exercises, it can take those an expression, like for example here on the modify ETL, and just assign it to a field. And so majority of things that happen on the switch is really just mostly lookups and assignments. There's very little math that is involved in reality, but you know, we do have addition, subtraction, there are shifts, there are like typical logical operations like bitwise XOR, XOR, then, and so on. Then there are a number of very powerful operations which allow us to manipulate headers. So there's add header. So for example, the packet comes in, it's an IP packet, and you would like to send it to a tunnel. So you might want to add another IP header. There's also a remove header if you want to do tunnel termination, and there's a copy header. And so remember how I said that if the parser parses the header, it sets the validity bit at the same time. So what the add header does, initially the header maybe is not valid, right? But then you say add header, and that sets the validity bit, and suddenly those fields become available to you. Again, for example, the spec doesn't say what would be the values inside those fields, so I would say you probably need to set them all if you want to get a reasonable result in a portable manner. Something that I would like the spec to clarify. There is also an operation called push and pop. Those allow you to deal with the header stacks. Then there are a couple of actions I should have put more.
Quick question. Push and pop, how do they differ from remove header and add header?
Well, so what they do is, so suppose you parse the first VLAN tag, and so it was VLAN tag 0. When you do a push, that becomes VLAN tag 1, and VLAN tag 0 is added. So they move.
And if you were to do add header in that case? If you were to do an add header in that case, adding a VLAN header, what would happen then?
Adding VLAN header on this, if VLAN tag 0 already existed, then when you do add header, it will just do nothing.
see. So interesting.
Yeah, because it already is there.
You would need to do a copy header from 0 to 1 and
Yeah.
then initialize it.
You can do that.
Hmm.
But it's easier if you do just
Okay.
So the art header only be invoked when you've already defined.
yes.
Okay.
Yeah, because again, remember, so we said that you should be able to send out only the packets that you can understand, which makes sense, right? If I'm talking to you, I should be able to understand what I'm saying, right? So that means that if you want to send the tunnel packets out, you should be able to also receive and parse them, so it's in your parsing. So the other actions are very, very interesting. I forgot to add the other ones, but I have on one slide, is count and execute meter. So if you have counters defined, that is the action that actually requests the counter to be incremented. And so execute meter allows us to obtain the color for the packet, and I'll show you some examples there. And this action, generate digest, is basically allows us to communicate well, or in some fashion I would say, with the control plane. So what this action does, it can take a certain list of metadata fields, pack them in some target dependent format, and send them to the control plane. So for example, if your packet is not in the L2 table, in the destination MAC table, right, or in the source MAC table, depending if you want to do source learning, it's not in the source MAC table, right? You can generate a digest containing the MAC address of the packet and the port it came from, and for example, VLAN ID, right? And send it to the control plane so it can learn the address. And the last ones are all about doing the loops inside the device. So there's resubmit and recirculate, which basically take the same packet and put it another time through the device, either ingress to ingress or from the egress. And then there's a clone when another copy of the packet will be created and sent where it's supposed to go.
I don't see a way to send the packet to the CPU.
To send the packet to the CPU, that's a very good question. In P4, there is really no particular concept of a CPU port per se. So what happens is on your target, you can say my port number 0 or my port number 64 or 512, whatever you like, is the CPU port. And so it's target specific usually, and that's the number that you just know that it's to the CPU. Yes.
In addition to that, so generate digest is also there. Right? So the receiver of the generate digest can be any object, target specific object. So if you want to capture a channel from data plane to the CPU through PCI or some special channel, dedupe channel or whatever, you can model it as a special receiver, and then you can use it. So there are more, there could be more target specific opcode channels.
Yes.
What happens if they have a full packet and you add header? What happens with the fragmentation and everything?
Okay. So yes, if you so the device itself and typically the switches, they do not perform fragmentation. But what they do, what will happen is that the packet length will increase. And so, which is actually another thing that is missing in the spec. It doesn't say what it does will happen, but I assume. Normally, in the other devices I'm familiar with, so the packet length, the device keeps track of that, and it will increase. And so, what you do is, usually on your egress side, you should have a programming which says, well, on this port the maximum frame size is X, and if the packet, then you have a construct, you have this if statements, right? You can compare, and if the packet length is more than X, what you would typically do, you will send it to the control path and let the control receive that packet, fragment it, and re-inject it back in the switch. That's how you typically do it in those situations. question. Okay. So this,
So what if you receive a valid packet?
So if we receive a valid packet, there is a construct called parser exceptions. It's in the spec, I didn't put in the slides, but it is possible for the parser to generate the exception, and also that constitutes part of the standard metadata that is parsed in the egress pipeline, and so you can say if the packet wasn't valid, I just don't want to deal with that. Anything of that nature. Action execution semantics is kind of, it's not a controversial subject, but it's like an area that changed significantly. So as of version 1.1 RC, the action semantic is that all those primitive actions will be executed sequentially. So if you think about this particular test, right? So both A and B will be 1. Right? So 1 will be assigned to field A, and field A will be assigned to field B, becomes 1. So prior to version 1.1, the execution semantics was parallel. So that means that A will become 1, and field B will be whatever the value was inside field A, because they would be executed in parallel. So you would think that the values would be latched, and then each statement will proceed. So in terms of practical implications, compiler should be able to parallelize by just checking the dependencies as much as it can. And then, on the other hand, you will be able to write, I think the action that you write will now be way more readable. So that's good. Okay, so how many steps will be supported per action? Depends on the target, right? If it's a software target, probably as many as you want. If it's a hardware target, probably very few. Okay, so this brings us to the most fundamental. Yeah.
Go ahead. Sorry, I just wanted to stand up. Sorry for that.
This brings us to the most fundamental piece of the whole pipeline, is the match action units. So we have actions. So what match action units do, they kind of match certain metadata and execute those actions, right? So so inside those match action units, we have tables. So those tables perform the match. So tables are fairly abstract in P4. So what you think, the way to think of them is really like tables, like those rectangular data structures. They consist of entries. And so each entry has 3 fundamental parts. So the key, what do we match on? The action, what would you like to do if there's a match? And then the action data, the parameters of the action. So to make it more specific, what I decided to do, a very protocol dependent picture. So you can imagine there is some switch in the middle. There are some workstations connected to that switch with the typical addresses 192.168.1.1. There is some server hanging out of this switch, right? And there's some cluster which is connected to the switch through multiple links. So we might want to do ECMP here, for example. Equal cosmic, multipath. So if we look at a very, very, very simple match action table, we probably would like to match based on the destination IP address, right? And so for each IP address on this picture, we can very, very easily decide what we want to do, right? So there are multiple actions that are available to us, but for each given address, for each given key, we need to choose one, and we should be able to, right? So for example, if you want to go to this host 192.168.1.1, the action probably would be you need to L3 switch the packet, and the parameters for that action would be the port number and the new source MAC and the new destination MAC and the new VLAN ID maybe, right? So that's what we have here. I didn't put any particular values, but you can imagine they will be there, right? Who knows what they are? It's your control plane, but the control plane should be able to choose the action. Same way for 192.168.1.2, right? Again, the action will be L3 switch. This host I decided to isolate, so I decided that, you know, again, my control plane effectively, can decide that for this particular address I will use the drop action. And so on and so forth. So maybe for the address like 192.168.1.254, which is the IP address of this whole router, I want to get the packet to the CPU, but I do not want to really L3 switch it, because if I L3 switch it, I will replace the destination MAC address and the source MAC address, which is typically a bad thing to do when you get the packet to your stack. You want to get the packet in the original form. So I will do another action called L3, L2 switch, which just requires the port number. So for each of the keys, you should be able to choose the action, and based on the action, you'll have different action data, different parameter lists. All depends on the action. Is that okay? Everyone understands this, right?
Yeah, going
question.
back to the L3 action,
Mhm.
so it's made up of at least 4 primitive actions, each of which modifies these action data.
Yes.
And you said that they execute in sequential order, but in this case, it would the compiler just know that the kernel for these are independent LS.
Yes, that's correct. So, and I will look at the code for the actions in a moment. So, hold on your question till then, right? So, let's take a look at those actions, how they can be written. So, for example, a 3 switch action, what we'll do is we'll copy the port number into the egress spec field. That's the standard field for the standard metadata field, so that's where the packet should go. We'll specify UMAC-DA, UMAC-SA, change the VLAN, and decrement the TTL. Right? That's the typical things that you do when you perform L3 switching of a packet, right? So, as Lisa just mentioned, all these fields are independent. So the destinations are different, the sources are different. So this can be easily parallelized, even though we say it's sequential semantics. No one cares. And that's the reason why we really decided to switch, because majority, like the vast majority of the actions, they look like this. So they're very, very easily parallelizable without any penalties. So when we want to do L2 switch, the only thing we need to do is just change the port. We don't need to change the packet itself, right? The L3 drop action, it just uses the standard drop primitive, but it could have been a more elaborate. For example, we would set certain bit and then perform a drop at the end of the pipeline. It depends on how you write the program. And there are a couple of other things that you can do. So for example, I decided to have a more realistic switch next hop action where you don't modify the packet immediately, but you just specify the next hop index, and then there should be a separate lookup in the next hop table from where you will retrieve those parameters. That's a more typical arrangement. And then there's the switch ECMP action. I will use the same field in the metadata called next hop, but there's a separate field called next hop type. And that will be set to different values based on whether this next hop contains a next hop ID or the ECMP group ID. So that's typical optimization that people use to kind of save some space in the metadata. That's usually a very critical resource in real switches. Yeah.
The previous slide. You might have already mentioned this,
Mhm.
but so where do those parameters come from? The port, the MAC?
So the values for the parameters.
Right.
So the values for the parameters typically come from your control plane, right? So what will happen? Let's kind of think through that. So how would the control plane know anything about this host 192.168.1.1? So probably that host at some point of time tried to communicate with someone, or someone tried to send a packet to 1.1. So this control plane, the say Linux networking stack, did not have this entry, or does not have this entry yet. Okay, but what it's supposed to do? It's supposed to send an ARP request saying who has 192.168.1.1. And so this host probably will receive, because this request is supposed to be broadcasted, it will receive the ARP request and send the ARP reply back saying 192.168.1.1 is that the MAC address, whatever the MAC address is, and it knows its own MAC address, right? So then this packet comes in, the control panel, control plane, processes the packet, right? And then it creates this because it knows, aha, the packet with this MAC address, it will be MACDA, right? Came from this port number 5. So I'll put port number 5 here. MAC-SA, that's my MAC-SA. Well, that one I know, okay, no problem. And, you know, because we are in the VLAN environment, it also knows which VLAN the communication went on. And so that creates, right? So in that regard, you will see that I also did, what I also did, I put this route, 192.168.1.0 with the prefix 24, and I said L2 switch, L3 L2 switch action. Why did I do that? Well, because typically what will happen if someone tries to send the packet to say 192.168.1.20, right? That is not here. I don't know where it is. The packet will come to the CPU running the control plane here. What the CPU will do, it will send the ARP request, and we're back to our story. That's how those stacks work. Okay. Yes?
And the control program can change the action dynamically?
Yes, control plane is able to change the action dynamically, so all it needs to do, so all these tables, they're actually very easy to operate. Effectively, what you need to do, you need to be able to add entry, delete the entry, list all the entries, and also there is an operation called modify. So you'll specify the same key, or you'll specify the entry handle, depending on how you structure the API, and you say, well, you know what, for this one, this became a bad guy. I don't want to do L3 switch anymore. I'll use the drop action. Fine. So, and that's how all those stacks operate. Okay, so here's the declaration for our host table. So what we'll do is we'll use exact match. So typically, the typical L3 tables nowadays, they contain 2 fields. VRF, virtual routing forwarding interface, right? And the destination IP address. Again, if you like at home, you don't use VRFs. Everyone is the same VRF. But in real systems, where you have multiple tenants connected to the same system, right? They might have the same IP addresses, so it's important. And here's the list of actions. So I don't know why, but sometimes when I talk to people, they kind of think that you can execute all, and they ask like, how will the data plane choose which action to do? And the answer you now know, right? It is when you match a certain entry, the entry tells you that is the action. It cannot tell you 2 actions or 3 actions. It only gives you 1. And that's how it is a very, very important fundamental principle.
Why is it 1 and not maybe a combination?
Well, so if you want to have a combination, it's very easy. Just create an action which has more parameters.
So for every subset of keys that you may want to change that,
You might. And sometimes you might have an action, for example, where you have like L3 switch, but then it might have another couple of bits saying, do change MAC, or do not change MAC-SA, do not change MACDA, right? And so people would set those bits to limit, so you still have one action, but it has like a multiple subvariants effect.
Can you have a condition inside that action?
Can you have a condition inside the action? Depends on the target. So this is something that right now has not been standardized yet, but potentially you would be able to.
So what's the reason to have the action, as in does the compiler actually make use of the actions somehow? As in, so you're anyway going to pick one among the actions that you're defining in your
Well, it tells you the list of possible actions, right? And the list, the reason the compiler needs to know the list of possible actions is a couple things. So one, the most fundamental one I think is, based on the actual action that you have, it will be able to calculate the maximum size of your action data portion, right? Because, and that will affect the placement. Now, say in certain devices also you need to make sure that the code for the actions is located in the same match action unit as the tables are, right? So if you try to just take the whole list of all your, I mean, it's not like in the chip there is like one place where you put all the actions, like the text section in the C code, right?
Sure.
They have to be very long, so that's why. Yes?
The reads, under reads the matches are in sequence.
So, good question. So how is the matching performed? So in this particular case, it says exact match, and so we do not really specify the algorithm. As long, if it's an exact match, there should be only one entry in the table that matches. Now that's another thing which is a little bit, I would like to see in the spec being kind of finalized. Right now the spec doesn't say that the control plane is prohibited from inserting two fields, two entries with the same key, but that is kind of obvious, right? So you're not supposed to have the same key in the table twice, right? So if you're familiar with SQL, right, they have a concept of a primary key in the table. One of the fundamental properties of the primary key, is it cannot be, there could be no possibilities. Same thing.
The exact match is if you hash the value first and then you hash where does the hashing happen?
Well, how this is implemented can be implemented in a variety of ways, right? So if you are in a software implementation, you can have a linear search, or you can build a hash, and maybe it's a hash with the actual buckets with lists, right? So then you go through those lists. If it's in the hardware, typically people don't do lists, but they use either multi-way hashing or something like that. They could be like one hash and then a fixed number of the bucket of a fixed size. But they have to, typically what they need to do, they need to store the key in the memory as well. So even though you did a hashing and you got to the right bucket, you need to compare the actual key so that you don't mismatch, right?
So where do you calculate the hash? Is it,
Where?
Yeah. Is it like before the table is matched?
Uh,
Before the table or like in Parser?
When do we calculate the hash? Well, I think the spec is totally oblivious to that, but I think it's conceivable to think that each table needs to calculate its own hash because the set of fields for each table is very different. It does make sense to calculate the hash of each individual field and carry it, and then try to use it. I mean, it sounds like a waste, right? So I would, I know how hardware does it, and that's how it does. But even if I didn't know, I wouldn't think that. I would just think that each table will calculate its own hash. Okay. So. One thing that can be done very easily in P4, you can change the type of the lookup. So here we had exact lookup. Here I decided to change and do LPM lookup on the IP address. So this one is more like an ARC table, right? Because it has the exact IP addresses here. This is more like a routing table. So VRF, I still use the exact match. The IP address, I use LPM. Now, there were a couple, I thought there was a question before, what to do when there are like fields with different matching. So, I would say that that's, so LPM is a little bit special. The spec explicitly prohibits you from having more than one LPM field. And the implementation can vary a lot. There are lots of implementations, especially when you do LPM, it might not even be a TCAM. There's another method called algorithmic TCAM, or algorithmic match, which is totally different, and it handles, say, exact match on VRFs totally separately from the routes. You can place it all in the TCAM, but what's important is when we generate the APIs for this table, right, we explicitly prohibit people from specifying the mask for the VRF. So logically, we still say it's an exact match, even though in the TCAM we might be installing the entries with like all Fs in there. And that's important because when people write their code, their control plane, right, they assume certain APIs. If those APIs start changing underneath, because we changed our implementation of the table, it becomes very inconvenient. So here, the language allows us to better express how the APIs are supposed to be. What is your intent versus implementation? And of course, you can change, and you can say, well, everything is allowed, and then you can do a ternary match on the VRF as well. So you could see down there, I kind of showed the logical view of those tables, right? So for the LPM, the prefix itself would define the priority of the entries. In case of ternary match, you really have to have a prefix. The priority specified separately, otherwise you don't know which entry is more important than the others. Okay, so I'll skip this example. It's the same thing but for L2. So that one will skip. So these are the types of matches that are available in P4 right now. So there's exact ternary. There is a separate thing called valid match. So you can check if a certain header was valid and also make your decisions based on that. And there is a range where you can specify min and max and different devices. And for software, it's very easy. For hardware, it's more difficult, but also possible. And so some hardware devices do that. Now, very close to tables, or to actions, I would say, there are some most interesting ones involved the keeping state. And there are like 3 entities that allow us to keep state so far. Counters, meters, and registers. So they're all a little bit specialized. So counters are the simplest. So you can imagine that, for example, I have some table which represents access control list. So I match on the typical 5 tuple, and then I can, deny packets or allow them to go, and so on. And so I would like to just count how many packets of which kind I got. So what I do, I can do. So this is my ACL, and then I can declare a counter, and it has a direct type, and it's tied to the table IP ACL, right? This table. So what it means logically is effectively my table got extended. So each entry now has a counter which counts packets and bytes. And so every time a packet matches a certain entry, the counter will be incremented correspondingly, and then control plane typically has the APIs to retrieve those counters, and we can examine them, print them, decide whatever we want to do. So this is a very easy to understand concept, obviously.
So
yes?
Packets and bytes is the type. Why are they like?
Packets and bytes is because logically there are 2 counters, right? So every time a packet goes through, one counter is always incremented by 1, and the other counter is incremented by how many bytes were in the packet.
Why not have 2 separate counters? Why are they like conjoined them this way? It's very odd.
It is usually, I think it's a matter of kind of practical convenience. I would say that the language has packets, it has bytes, and so you probably, I don't see any rules in the language why I wouldn't be able to declare counter, IPACL stat bytes, and say, so have multiple of those counters directly attached to the table. But typically, those counters do come in pairs, and when you want to do things like, for example, quickly get them through DMA, it's nice when you know that is kind of a special counter, so that you can optimize things and get them all together. So, yeah.
So the other related question is, why not just say packets and bytes IP address tags?
Huh?
Why not put the type as a keyword, like packets and bytes? So instead of saying counter, just say packets inputs. Just
Why not to make the counter an attribute to the table?
No, sorry. So instead of writing counter, like IP equals stacks, and then say this is the type of the counter. Why not just say packets and bytes and then say the name of the counter? So make that a primitive type instead of having type as an attribute of the counter.
Well, I think that the reason is because there could be many different counters that count different type of things. So it's kind of, I think counter is more fundamental than what it counts, right? So it could have been done that way, but I think counter
it's a minor comment.
Counter is more fundamental than what it counts. So these counters are called directly attached, meaning that each entry in the table has a corresponding counter. Sometimes it's very convenient. Sometimes you might want to have a more flexible arrangement, and that's where we have indirect counters. So imagine another table. This one assigns a broadcast domain based on a port and the VLAN combination, and we want to count how many packets belong to which broadcast domain. So here's our table. And so what we'll do, we'll create an array of counters. And so just again, those counters will count packets and bytes, and we'll say how many counters will be there. So effectively, you can see a table is on the site, which has so many counters in there. Now in our action, set broadcast domain, we execute two primitive actions. So one is modify field, where we assign the broadcast domain, and the other one says count. So what it means is that inside each of the entries in this port VLAN table, the action data consists of two pieces, broadcast domain and broadcast domain stat index. And so what will happen is, for each given key, right, we'll increment a certain counter. So you can say that if I assign broadcast domain 5, I want to increment, say, counter number 3. You can also say if I assign, say, broadcast domain number 10, I also want to increment counter number 3, because I want to count them together, right? You can also remember that this index can be calculated. So for example, you can have multiple counters for each VLAN. Say you want to have each separate counters for each VLAN priority or something like that. You can do that because you'll take an index, add the priority, you have the combined index or something like that. So it's a very, very powerful construct. And the last one is, it is also possible that there's another table which maybe assigns VRF or something like that, and it can potentially share the same counters, because whoever uses this count operation has the access to the counters.
So physically, are those counters on the same table stage, or where are they located?
Where those counters will be, it really depends on your target area, and there could be a number of things. Like for example, if you take tables which are like in totally different places in your pipeline, and you say want them to increment the same counter, sometimes the compiler says, oh well, and I have to put this table really far away, and this will kind of move your whole pipeline. So I mean, you have to be aware of what are the capabilities of the target.
But you can refer to the same table from different.
Yeah, and typically you wouldn't do that anyways. Like semantically, it makes sense really if you kind of do similar things you might want to share those things. Yes.
What's the difference between this static and direct?
Between
this flexible, static and direct?
So the difference is that with static, I'm sorry. So with static, you explicitly say that the counters can be referred only from one table. And with indirect, they can be referenced from many tables. So static is kind of more restrictive and allows better compilation. Okay, so meters, they're declared in a very, very similar way. So You again can have direct meters, which are part of the table, and you can have indirect meters, which are queried explicitly by executing the action execute meter. So, anyone knows what meters are? What they're used for?
No.
No. Okay. Okay, so meters are typically used to meter the rate of packets, either in bytes or packets per second. So here's how they are implemented, typically. So the simplest meter, so how, just think about that. You want to allow a certain rate, so many, say 100 packets per second. How would you do that?
Token bucket?
You need to use token buckets, exactly. So what it is there is a bucket, it has certain height, and there is like a faucet from where those tokens drip. So if I want to send, want to allow 100 packets per second, that means that I need to add 100 tokens per second. I can add one token every hundredth of a second. That will make my meter as precise as possible. I can add, 100 tokens once a second, and that will be really not very good. Right? So we add those tokens, and every time the packet passes through the meter, it removes a token. So if there are not enough tokens in the bucket, the packet is not allowed to go. So that allows you to maintain rate even if there are bursts of packets, as long as there are tokens added regularly and the packets come in, you will get average rate of 100 per second, 100 packets per second. Now, there could be a situation where from time to time there's a lot of packets like line rate. Okay? It's called a burst. So what you do, you typically declare the other parameter of the bucket. So this is rate. It's how wide your faucet is. And this, how high is your bucket. And that's burst size. So in your bucket, you might accumulate 100 or 1,000 tokens, how much capacity you have in the system. And once, if there are no packets for like, 1 hour, the size of your bucket will be 1,000 tokens. So that means that if at some point of time, suddenly 1,000 packets come at line rate, they're still allowed in because your overall rate will be very small, right? It's just that the burst. So that's the burst size. In the industry, people usually use two token buckets. They're linked together, but it could be one as a simple example. So the packet that came in and there were tokens in the buckets, it's colored. So this meters, they are really coloring machines. So if there are tokens, it's called green. And typically those packets will be allowed in. If there are no tokens, they will be called red. And then you can decide that you want to drop red packets. And as I say, in the industry, there are two token buckets usually linked together. So if you didn't pass through the first, but you passed through the second one, you'll be yellow. Okay?
So one thing to clarify is that this meter does not drop. It only colors.
Exactly. It's
So
a coloring
that
machine.
you can either drop, that's policing, that can be done later on in the stage.
Absolutely.
And also the reason why we're using two different colors is because if you use two buckets, the token drop rates can differ. That way you can actually differentiate between 2 or 3 ranges.
Yeah, so there are like a couple of standards. One's called like 2 rate, 3 color meter. So then they have separate rates. There's also a single rate, 3 color. Then they're only the burst size differ, but the rates are the same. So effectively, Chang just said what I wanted to ask you. But anyway, so here's the example of the action. So when we execute the meter, what happens is we check a reader with a given index, and based on how many buckets, how many tokens are in the bucket, the buckets, the color will be assigned to the packet, and it's just 2 bits of metadata. And so what do you do with those bits? Later on, you can match on them, or you can use the if statement, and then, for example, drop, and that will really create the real meter.
Drop or use
Or
low
drop,
priority
or
queue.
maybe copy the CPU, sum, and let the others to go through something. It just, your fantasy is the limit.
Question. So you
Yes.
can only declare 2 meters in your program?
No. So what you do is you declare, like on the previous slide, you see I declared like instance count. So what it means, graphically speaking, is you have an array from 0 to 999, and in here you have bucket 1, and it overflows in the bucket 2. Here you have another bucket, and it overflows. And all these can have totally different rates and burst sizes. Okay? The most generic piece of state is called registers. And so that's another thing that is, you might notice some discrepancy between what we tell here and the spec, but I think that will be clarified really soon. So registers, they're typically declared like indirect counters, but they also have width. And so what we can do here is basically there are 2 operations. There is read register and there is write register. If you read the register with a given index, the value will be retrieved and put into some metadata, and then you can do some math and whatever, right? And when you do a write, a given expression will be written in the register with a given index, right? So for example, here what I did, I had 2 actions. So start new flow. For example, we have an array of registers called last SYN. Last time we saw a SYN bit on the TCP, right? And so you can imagine that when you do a match, right, and you saw a SYN bit, you will store a timestamp in the register, right? And then if you do not see a SYN bit, the only thing you do, you just, for example, go and calculate how long was there since the start of the flow, right? You see the SYN bit again, you will modify here, so store a new timestamp in the register.